So let me introduce our speaker for the evening, Professor Xavier Prochaska. Professor Prochaska is a professor of astronomy down at UC Santa Cruz. He completed his PhD at UC San Diego and was then a Hubble Fellow at Carnegie Observatories in Pasadena before joining UCSC. Professor Prochaska is a regular visitor here at Lick Observatory. His graduate class at UCSC bring astronomy grad students to the mountain every year for an astronomy workshop. His research encompasses the nature of gas, both in and outside of galaxies, in the early universe, and tonight he's going to tell us how to weigh the universe.
Thank you. Thanks for coming. You all hear me in the back okay? Sweet. You can kill those lights. Thank you. So, my name is Xavier, Professor X if you want to be more formal. Xavier if you know your Japanese, which is where I try to spend 2 months of the year. I was just there, where, this is the only time I'll mention COVID. It was absolutely raging. I tested on Monday. I think I'm good, but if you all don't feel safe, I'll keep over here. Welcome to Lick Observatory. What was not mentioned also, I was associate director here for 2 or 3 years, about 5 years ago. So I have spent a lot of time up here. I love it. I really love it. Hopefully you're enjoying it as well. You've seen some of the sunset. The beauty up here is unmatchable. And I love these visitor events. I love looking through the telescopes. You'll get a chance to once it gets dark enough. So I'm here mainly to entertain you until it does. Hopefully I succeed. If not, tell me. Okay, and I'm going to hopefully teach you a little bit about how we weigh the universe, which sounds kind of crazy, and it is, but here we go. A few words about me. You heard a bit of my bio, so you'll see it again. I was a PhD at UC San Diego. Then I was what we call a postdoc at Carnegie in Pasadena, and I've been faculty at UC Santa Cruz. Did I grow up in California?
Yes.
No. I was born in Newport, Rhode Island, and where the tallest ships are, and where the America's Cup used to be raced. But lived in South Kingstown. If you know your Rhode Island, you probably don't. I got my PhD, my undergraduate degree at Princeton, also on the East Coast, and then moved to California, where I've been ever since, including the PhD in UC San Diego. I'm a professor of astronomy. I'm also a member of the UC Observatories, which is headquartered at UC Santa Cruz. So we operate and own Lick Observatory. We also operate the Keck telescopes, which you saw on the first slide, and they'll feature in this talk as well. And crazy fun fact, I'm also becoming an oceanographer, but you can ask me about that if you want. You won't hear me speak any further on it today. This starts the talk. What are we looking at? Silver and gold, fantastic. When you see silver and gold, what do you think of? Money. When I see silver and gold, as a scientist, what do you think I think of? It's not money. I am paid well. Thank you, taxpayers. Elements. I do think of elements. And that's kind of where we're going to be talking about throughout the talk. Effectively, all of the elements. This talk is about all the elements. We're going to give a name to them in a few minutes. But there are silver and gold in the periodic table. If you're too old to remember what the periodic table is, or if you're too young to have seen one, there are silver and gold. Here is a periodic table generated by a colleague of mine, we used to hang out together. She's in Ohio State, Jennifer Johnson. She has color-coded all the elements in the periodic table by where they came from, or where we think they come from. Some of them I'd say we know for sure. Some of them we might be a little bit vague on. And so silver and gold, which are, let's see if this laser thing works. Oop, yeah, it does. Silver and gold are right there again. And they're orange and yellow, which means we astronomers believe they came from stars, and specifically dying, explosive, low-mass stars, and merging neutron stars, which is a whole talk in itself. Exciting. For the next 15 minutes. I'm going to focus on the blue color, the dark blue, not the light blue. I don't know why she chose two shades of pretty similar blue. Here we go. The dark blue. And if you can't read in the back, that says Big Bang Fusion. So who's heard of the Big Bang? Good. Great. It's our well-evidenced theory for the universe, the formation of our universe, start of our universe, whatever you want to call it. And the element's colored dark blue, so that's H for hydrogen, helium, the second element, and then you can't see almost anything else that's dark blue. All right, the rest of these are light blue, trust me, except a little bit of lithium. We believe those were made 7 minutes after the Big Bang. All right, 7 to 10. Started at 7, finished at, does anyone know when it finished? Do we have some? Finished when neutrons decay, which is about 50, well, we don't know precisely, we have a good estimate, about 15 minutes. So, first 15 minutes of the Big Bang, but not the first 7 because it was too hot, and then it got just right, and then neutrons went away. All right, so we're going to talk a bit about Big Bang nucleosynthesis. That's what we call that, the formation of nuclei during the first 10 minutes, say, of the Big Bang. And I'll explain to you why I'm so interested in that. So those elements. Baryons. So as a scientist, I call the whole periodic table baryons. And that's probably it's not quite accurate. It's not quite accurate. This is an accurate definition. Do not read it. It'll make your head hurt. It doesn't quite make my head hurt, but it could. When I say baryons, think periodic table, okay? I'm going to say that word baryons. It's Greek. It means, I just looked at it. Oh, and I already forgot. Heavy. I think it means heavy. But don't think that stuff, which is the accurate definition. Think periodic table. Think this. Baryons. Baryons. We are going to weigh the universe's baryons. What are you made out of?
Star stuff.
Good. What else do we call it as scientists? What are you made out of? What are you made out of? What are you made out of? Matter. What do we call that matter?
Baryon.
Thank you. What are you made out of?
Elements.
What are you made out of?
Baryons.
Baryons. What is this chair made out of? Baryons. The floor. The walls. The air you're breathing.
Heavy stuff.
Baryons still. Okay? So when I say baryons, think ordinary matter. It's the stuff you're used to. I imagine some of you have heard of dark matter. I'm happy to talk about that in the hall. I have given many a public talk here. It's probably my 20th public talk, maybe not quite that many. I've talked about dark matter before. Not tonight. Tonight you get baryons. The ordinary matter. A cosmological question. Cosmology is the study of the grand universe. A fundamental question of cosmology is how many baryons are out there. You might like to think, is there life out there? I'm not going to talk about that either tonight. I don't know. Probably. Almost certainly. But I don't know. Okay. How many baryons are out there? People seen this image recently? Pretty exciting stuff, huh? Yeah. I put it in there just for the galaxies, and stars. What are stars made out of? Good. Galaxies? And? Dark matter. Uh-oh. I said I wasn't going to talk about that. Forget I said that, right? But normal matter. In science, we use that Greek letter, omega, and that little b to signify baryons, to describe the mass density. So how many baryons there are in some little volume, say cubic meter, in the universe. You won't see that too many times, but baryons, we're going to measure baryons. All right, let's do that. Keep talking about it. Big Bang nucleosynthesis. So there's going to be 3 ways. That was the title of the talk, right? 3 steps, or maybe it should have been 3 ways. One is to use what we measure or infer about what happened in the first 10 minutes of the universe. It's pretty amazing when you think about it. Big Bang nucleosynthesis, that's what we call it. And the focus is on this type of hydrogen, deuterium. You might have heard of heavy water. Ever heard of heavy water? So there's normal water, and then there's heavy water. There's not light water, I guess. There's water. The water we are accustomed to is that water. It's hydrogen with one proton and an electron. But hydrogen can come in another form, one proton, one neutron. We call it deuterium because there's two nuclei. And if you have heavy water, it's either because you've got deuterium in that water or both deuterium and tritium or just tritium. But you've got some of these isotopes is what we call this. All right, so why am I talking about deuterium? Because we measure deuterium in the distant universe, and we use that to weigh the universe. I'll say it again. We observe with our telescopes, including the one that you won't see tonight because it's being used for science tonight, not the public. It's the 3-meter Shane. It's across the hill. That's why I'm pointing over there. You'll see that figured in the story. We use our telescopes to study how much deuterium is in the universe and then can use that in our understanding of this Big Bang nucleosynthesis to weigh the universe. This plot's a bit complicated. I'm sorry if you don't quite capture it all. Just focus on the orange curve if you can, the orange. If you're colorblind, it's the one I'm doing right there. And it's tagged with deuterium. And with this part of the chart is density of the universe, the thing we're trying to measure. So we're changing it here, and you can see how rapidly the amount of deuterium, this axis is how much deuterium. So down here, if I had a very low density universe, we would have more and more deuterium. If I have a very high dense universe, a lot less deuterium. That's it in a nutshell. If I can measure how much deuterium, if I can get this axis, then I know how dense the universe is. Let me pause there. Questions? Okay. All right. Don't be shy.
What is that chart based on? Who generated this?
Yeah, excellent question. So fundamental physics will be the quick answer. So what fundamental physics? Particle physics. What does that mean? How do nuclei form? We can measure that on Earth. And we bang them together and we see how they behave. It depends on cosmology, our understanding of how hot the universe was 7 minutes after the Big Bang. We actually measure how hot the universe is today around us. You'll see that in a number of slides, and can infer how hot it was at 7 minutes. So we have a pretty good handle on that too. And then a few other things, but those are the main two pieces. Yeah, great question. Please.
What do the orange balls represent? In order to
Anyone want to answer that for this young person's? What are the blue? Go ahead. Protons and neutrons. Which ones are the protons? The protons are orange because I need 2 protons to make helium. And so helium-3 will be the one with one neutron, excuse me. Normal helium is this one, 2 protons, 2 neutrons. Great question. Please.
This question might be so
No.
So did you say deuterium is the heavy water?
Yeah, well, it's a part of heavy water. You need oxygen too.
Okay. Because I'm like, water in the universe? Because you were talking about that's how you measure how dense, depending on how much water there is.
In this case, we're not actually using water. We could, to be honest, but in this case, we're using free-floating deuterium and free-floating when we compare it to the normal hydrogen. But great question. Yeah, we could use water maybe for the experiment. It would complicate things enough that people would struggle to believe it. But in principle, great question. All right, I'm going to move on. So there's going to be a lot of photos of telescopes. I hope you love telescopes because you should be here to look through telescopes tonight. That's why you're here, right? That is the Lick 3-meter, which is right over where I was pointing. And it figured prominently in this story as the Finder telescope, which I've labeled as finding the Goldilocks quasars. Quasars are crazy supermassive black holes that shine brighter than just about anything else in the universe. Talk about crazy. And my colleagues needed to find just the right quasar to do their science. And they came to Lick Observatory, they being these two, Scott Burrells and John O'Mara. He's the chief scientist at the Keck Observatory. He's part of a hedge fund in San Francisco. And they shot this laser and killed a whole bunch of stars and planets and then looked for the quasars. And they were really good at it. And then the Goldilocks quasar, they took to the world's largest telescopes, the Keck telescopes. And that's where they really did the science. So sifted through a whole bunch, found the best one, best two, best three, brought it to the Keck telescopes in Hawaii. Again, you all, who's a taxpayer in the room? You all can raise your hand. If you paid sales tax ever, you guys paid sales tax, trust me, you can raise your hand. You're helping support our usage of these telescopes on Mauna Kea in Hawaii. And they're the world's biggest. These are 10 meters. That's just about the length of the whole room for one mirror. Okay, it's 36 segments. It's a big telescope. And it's well sought after. You don't go there and just willy-nilly start pointing in random directions. You bring the best thing you got, and that's why Lick was used first. It's a very important resource in the game. This is the data. You may want to avert your eyes. These are spectra. Even to astronomers, I'm told, don't show spectra to astronomers. Well, we show spectra to each other. Trust me, the green dashed line is indicating where deuterium is. So the feature here, which I'm trying to scallop out, that's deuterium. I won't go into any more depth on that. And then we measure hydrogen from the really big feature here. And this is Lick data right there. Right there. That was taken in 1994, maybe, with the instrument that's on there tonight. I saw just a few minutes ago. So these are the data that let us measure that deuterium, and from that, weigh the universe. Approach number one. And the answer they determined, and got a really pretty good answer in 1998, is 1 proton per 4 cubic meters. So meters about yay big. A cubic meter is that big, right? So take 4 of those. That was 1. Take 4, which I could map out, and you'd have 1 proton on it, on average, in the universe today. So there's a number to take home with you. You can wow your neighbors. Look, Bob, this is 1 cubic meter. And if you took 4 of those, all right, I have more interesting neighbors, perhaps. Or more bored neighbors. I don't know how you want to look at it. That was number 1. Here comes number 2. And we're going to use measurement from the early universe again. Sorry about the static. I don't think I have any control over it. We're going to use a measurement from the early universe again. This is the cosmic microwave background radiation, the CMB. We like our acronyms in science. That's a map or an image of the temperature field of the universe, measured today. Okay, where red dots are patches of the sky where it's a little bit warmer, and cool dots are patches of the sky where it's a little bit cooler. And by a little bit, I mean 1 part in about 1,000,000. And does anyone know the temperature today? The actual value? Anybody? No? Close. He said 4 Kelvin, where 0, by the way, is that absolute 0 thing, as in you can't get colder than that. It's 3 Kelvin, close enough. All right, and then there's these little fluctuations that we can detect with our satellites. Yes, sir?
Where are we on that map?
We are on Earth, staring at the sky all around us. So you can do this tonight. All right, the sky around you is a sphere. You good with that? You good with that? And then have you seen a map of a sphere before? Yes, you have. You've seen maps of the Earth, and you've seen them projected like that. So we're doing a spherical view, just like you do of the Earth, but now it's the sky above you instead. And the center of our galaxy is in this map right there. There's nothing special here about the center of our galaxy in this view as it's been constructed. But that's where the center of the galaxy would be. And the center of the galaxy is about there or something right now. Great question. Anything else? All right, so the second technique uses this data. This came from the Planck telescope. It's the most, before it was the WMAP telescope, I considered the most fundamental measure of my lifetime probably in cosmology was data like this. And as humans, this is pretty cool. As humans, so this is the clearest image you can make of the temperature map. We can't do any better. You can build a bigger telescope, it'll look the same. As a human triumph, if you will, we have measured this map as well as you can possibly measure it in sharpness. That's kind of cool. Side note. All right, zooming in, that's as sharp as it goes. Again, if I had a bigger telescope, it would look this looks blurry. That's not blurry, that's the universe. To give you a sense, the measurement that we make to weigh the universe in this case is to measure how big these dots are. I'm calling them dots, they're not quite dots, but they're like dots. And the answer is that these dots are about 2 moons across, which is about 1 degree on the sky. So 360 degrees to go all around the sky in a circle. 1/360th of that is 1 degree. That's about the size of these dots. And from that we measure the mass of the universe with a lot of physics under it, which I won't go into detail on. And this gentleman showed, he wasn't the only one, Ryan Cook, and he's now at Durham University, that the measurement from the deuterium, which I told you first, and the cosmic wave microwave background agree perfectly. So the deuterium is this blue swath. There's that omega B thing I said would show up here and there. That's density of the universe in baryons. And then the gray is the other measurement, the CMB, and they land right on top of each other, and that's the little red is the consistency curve or whatever. And so to percent level, we have measured the universe 2 different ways now and got the same answer. Great. What impresses we scientists is that this was done with completely different data, completely different laws, not laws, but different physics that was involved in it, and you get the same answer. This is as strong of evidence of the Big Bang as I can give you. Okay, when I do 2 completely different experiments to measure the same thing and I get the same answer, both requiring the Big Bang, for me that's about as strong as it gets. Questions on that? No? All right. How are we doing on time? What time is it? 8:26. Good. All right. Doing pretty well. We're doing all right. 2 ways. Now comes the puzzle, and then there'll be the resolution. All right. All right. So let me go back here. I've said it. I'll now re-emphasize. Both of those measurements came from the early universe. One was 10 minutes after, right? And the other, I didn't tell you, CMB, the radiation from our universe, that was released 300,000 years after the Big Bang. Which, okay, may sound like a lot, 300,000 years. But today we're at 14 billion years. So that's early universe too. Right? Where if I had asked this young lady, I think, in the front row or second row, how to count up the baryons in the universe, you might have said, well, just go out in the backyard and count them. What are you doing? Messing with deuterium and radiation fields and all that nonsense. So we did, or a colleague of mine did, Masataka Fukagira-san, who will appear in a few slides. We use telescopes like this. This is in New Mexico. This is the Sloan Digital Sky Survey telescope at Apache Point to count up galaxies. So we take images of the sky. That's a cheat. That's from the Space Telescope again, but so nice. We measure galaxies, observe galaxies, count them up, and make an estimate of how many baryons are out there in galaxies. Straightforward enough. We take radio telescopes. This one's also in New Mexico. This is the Jansky Very Large Array. And we use those telescopes to count up the hydrogen atoms that were in the periodic table, which are also in galaxies, but they're not the stars in galaxies, they're the gas in galaxies, so it's a different component. And here are some maps of gas in galaxies. They're pretty pretty from that telescope. So we count up hydrogen atoms. We use this telescope, which is in Chile. This is called the Atacama Large Millimeter Array, ALMA. It's at of order 20,000 feet. Not a fun place to be. but a good place for telescopes. We use that to count the molecules in the universe. Mainly hydrogen again, but in molecular form. And they look a lot, the molecules are in pretty much the same spot as the rest of the gas, so they look a lot like the last slide you saw, but the molecules in our galaxy, counting up those baryons in our backyard. Then we use an X-ray telescope, this one's Chandra satellite, to detect hot gas in the universe. How hot, you ask? How hot? 1 million degrees, even 10 million degrees. So hot that it emits X-rays. And they love to color it purple. You cannot see these photons. These are X-rays. But there's a lot of hot gas in clusters of galaxies, some of the biggest, most massive structures in the universe. So we count that too. All right, so let's recap. Galaxies from their stars, hydrogen gas from the radio telescope, molecular gas from a kind of radio telescope, hot gas from the X-ray telescope. And so Fukuguta-san in 1998, when he heard about the deuterium measurements, said, oh, I know how to count baryons in my backyard, so I'm going to do that. And he did. And all the stuff you could count are these wedges. So I've gone through them, stars, gas, the black is the cluster X-ray gas. And he was left with a Pac-Man that ate it all, and said, which was missing, undetected. That's troubling, right? I just told you, oh, triumphant Big Bang, it's the best. Right, we got the right answer, and then, okay, our backyard, we can't even get half of the baryons? Compared to that number, I said 1 proton per 4 of those cubic. We came up more than half short. We were getting less than half of 1 in that 4 cubic meters. That's embarrassing. It should be easier to do it in our backyard for a number of reasons. But it's not. Well, apparently. So that was published in 1998. I was what they call a postdoc at the time. I guess you heard my bio in Carnegie. A whole bunch of us astronomers think we're smart. We'll go find these baryons. We spent 20 years searching for the baryons. We used the Keck telescope. We used the Hubble Space Telescope. We used this telescope that no one's ever heard of. We used the Chandra Space Telescope. We probably spent $50 million of your money. Sorry, send me the bill. We did good science along the way, honest. But then they all failed. 20 years. What the hell? So we definitely need a bigger boat. Maybe a bigger telescope. No, we need to be smarter, or in this case, get a little bit lucky. We didn't use a bigger boat. We used an older telescope. We used this telescope. Well, this started it off. This is the Parkes telescope in Australia. It's a radio telescope. Clearly built in the 1950s or 60s, right? Nice architecture. And a scientist who you'll see in a slide or two, okay, discovered something with that telescope. He was looking for pulsars. Those are rapidly spinning neutron stars, if you know what those are, which pulse, surprise, which means they give a burst of radiation, radio light really, well, depends how fast they're spinning, but say a millisecond. Spinning fast, like a lighthouse, you get this flash of light every millisecond. He was searching for these. He was searching for these in our neighboring galaxies called the Magellanic Clouds. Who's seen the Magellanic Clouds? Only 1? 2? Who's been in the southern hemisphere? Only 1, 2. I don't know, that explains it. Oh, you might have seen them then. You can only see them from down on the other side of the planet. The Earth is not flat. There's another hemisphere down there. Trust me. It could. It's not. Trust me. And he detected 1 pulse, not the series like you saw for the pulsar. 1 beam of the lighthouse, and then the lighthouse broke, or who knows what happened. And it looks like this. I don't think I'll even go through it. That's how the data looks. If you're interested, ask me. Duncan Lorimer is his name. It's a cool story. In fact, I think I'll just go back to that. He detected this. It was totally unanticipated. It was serendipitous. He was looking for the pulsars I just showed you. He was looking for this. He saw this. He said, what the? And it was accidental in the sense that he had actually even changed the software and screwed up, and this popped out, and he's like, oh, wait a minute. I didn't even mean to do that. And he didn't dismiss it, which he could have just done and said, all right, I just screwed up. I'll ignore that. He dug in. He took a while to convince his colleagues, 2 of his colleagues, to even write a paper about it. And we now today call these fast radio bursts, FRB. I'm going to use that acronym, fast radio bursts. They're detected in the radio. They're a burst of radiation. They last for about a millisecond, sometimes even a lot less. That's the fast part. So what, you say? Well, I have a movie to impress you. It's to describe what's called the dispersion measure. All right, you're going to see light travel through the universe. You're going to hopefully hear some really cool sound. And you'll see that the different colors of light separate as they travel through the universe. That's what we mean by dispersion. Think prism. Prism disperses light. Well, here the universe is doing the dispersing for us. Maybe I don't have to go over there. Does it just do itself? All right, here we go. There's the burst. There's the light. It's approaching some gas, some electrons in particular. And the redder light travels a little slower. More gas, more separation, more dispersion, that's the word we use. That light's then detected by a radio array of telescopes down in Australia, which I'll come to later. All right? I know it's a cool video, huh? Remind me to go back when I get back to ASCAP. So, dispersion measure. That spreading of the light is entirely due to the electrons that you travel through. So it's an electron counting machine. And for every electron, there's a baryon. So it's a baryon counting machine. It's the only way I know to measure all the baryons. And so the 20 years of failure, here's the option to go forth. Now, he detected that in 2007, and unfortunately, shortly thereafter, they detected a number of other things that looked like fast radio bursts. They were the microwave oven underneath that Parkes telescope. And at lunchtime, they would generate a fast radio burst. And that was puzzling and upsetting and led part of the community to not believe anything for a while. That happens. Emily Petrov used the same telescope to then identify a few real bursts, real signals that nobody could explain with microwaves. It was also determined it was the microwave was an issue. Stop using the microwave. More FRBs were discovered. Arecibo in Puerto Rico detected multiple bursts from one of these sources. We call a repeater, like a pulsar, but not regular, like a pulsar. But still, multiple bursts. Lauren Spittler led that discovery. That's what Arecibo looks like today. So sad. Oh well. The NSF was trying to kill it for many years. Maybe they even did it, I don't know. Anyways, it repeats. They were able to point this telescope, we're back at the Very Large Array at it, and localize it on the sky to a very, very small position on the sky, which let us then say, this is occurring in a galaxy. And that little smudge is the galaxy. Let's see it again over here. Keck telescope imaged that patch of the sky where the radio light came from. And this little dwarf galaxy's the host, that's the word we use. The source of these funny signals, fast radio bursts. This is important because I can count the baryons with the dispersion measure, but I also need to know how far away the pulse came from, as you'll see in a figure So I need to have a measure of its distance, and the galaxy gives me the measure of the distance. We use redshift. I'm not going to go into depth on redshift. That's another part of a cosmology talk. We use spectra. This is a spectrum. The blue is us splitting up the galaxy light. Galaxies shine in hydrogen. They shine in oxygen. We use that to measure the distance to the galaxy. Okay. And I'm going to jump this movie. You can find it. Well, all right. I'm not going to. It's short. This is explaining, or supposedly explaining, how an expanding universe leads to a redshift, and so that you can infer the distance to an object. It does an okay job, but it's not the best movie. All right. So I wanted to measure how many baryons are in the universe. This is the universe from a computer simulation. Call it the cosmic web view of the universe. The universe, as we predict, has this web-like structure. The orange blobs are galaxies, or in this computer simulation we call them halos of galaxies, but think galaxies. And then everything else is gas in this universe. Intergalactic medium is the term we use. The stuff in between the galaxies. That whole thing is the cosmic web. If you love your equations, this is how we put this dispersion measure to work. There'll be a quiz on this afterwards. Make sure you pick it up at the front. But we're after the counting electrons, counting baryons, and what we need to know is redshift and dispersion measure, and those are the two things I can measure. Okay, so I measure that, and I infer that. Here it is as a plot. The x-axis is distance. We call it redshift, z. This is farther away, about half the age of the universe at this spot. And then this is that dispersion measure. And this is what we predict using deuterium, using that Big Bang nucleosynthesis. This is the line we predict for the universe. And some scatter about it. Is that correct? We've been using the Kraft telescope, these antennae, to detect fast radio bursts. Steve, why am I blanking on his first name? Bannister. Why can I suddenly not remember my colleague's first name? Well, you don't know him anyways. Bannister. Leads the project. We detect the fast radio bursts, we detect the redshifts, and then we were able to make this comparison, this third way to measure the density of the universe. And indeed, our measurements land exactly where the Big Bang nucleosynthesis said that they should, and exactly where the CMB measurements did. Now that we could actually count up the electrons sensitively, we can prove or match what we expected all along. It's gotten hot in here, holy cow. I'm done, more or less, 2 slides. My colleague who led this paper, sadly a week after it was published, passed away. We've named this whole plot, if you will, after him, the McCord relation. His name's J.P. McCord. And it set to rest this 20 years of searching for the missing baryons. We were able to find them using these crazy fast radio bursts. So, to conclude with full concordance, measuring baryons from deuterium, from Big Bang nucleosynthesis, measuring baryons from the temperature fluctuations in the universe, and measuring baryons from fast radio bursts, all in concordance, all in line with predictions now of our Big Bang cosmology. And with that, I'll end. I'll be happy to take questions until the next group comes by, but that's the end of my presentation.